So I wanted to make a quick video to go along with the student question teacher answer announcement I'm posting on the linear regression activity. And what I have on the screen here to start with is a graph of the moisture, the depth moisture data from the linear regression activity. This would be the second example. And so notice here as the depth the sample came from increases, the moisture content of the mud is decreasing. So this relationship between the variables is a decreasing relationship. But also notice how the curvature is opening upwards on this curve. All exponential relationships between variables have this kind of basic pattern. They're either going to be increasing an increasing pattern, which would curve upwards like this, but notice how the curvature would also be opening upwards. And we call this concave up, this shape of a curve. So I want to compare that now with the actual activity that you are being asked to do, the velocity output data. So I haven't even entered this list yet, and I'm going to go ahead and show those steps as well as a review. Keep in mind, if you already know how to do this step, entering the data into the calculator, you can always move forward in the video and skip over this part. So watch the buttons I'm pressing here. I'm gonna press the stat button, which takes me into the general statistics menu. And I'm going to choose edit because I need to enter some data. So this is the data editor now that I've just opened up. And notice I have the depth moisture data already entered, obviously. Otherwise you wouldn't be able to see we wouldn't be seeing a scatter plot. And what I'm going to do, now notice I moved my cursor all the way up to the top, and I'm now in the realm on the editor where I can do list operations. I'm going to go one to the right because I want to insert a named list. I'm going to go ahead and use a named list for this example. Now, it could be that your desktop looks a little bit different than mine, or your calculator screen while you're in the editor. And there are a number of different ways we can configure this window. In fact, just for fun, I'm going to go ahead and delete these two menus. Just all I have done is highlighted them, press the delete key. And notice, of course, I'm all the way to the top with my cursor, and what's being indicated is the entire set. That's set notation. The whole set's being selected. So I'll delete both of those lists from the editor. Now, the thing to keep in mind is just because they're deleted from the editor doesn't mean they're deleted from the memory of the calculator. In fact, those lists still exist in the memory, and we can get them back. That's not really the point of this video. So I'm going to go ahead and move forward and show you how to enter some new lists, blank lists, and how to give those lists names. To enter a blank list, again, cursor all the way to the top, not here, but up here. Press second, and then delete. The calculator has just inserted a blank list. It's waiting for a name. And I'm going to give it a name. Now I can press second alpha, and notice what I've done is I've alpha locked the calculator. So now I can just type keys that correspond to letters. I'm going to name this list velocity, or VEL. I'll abbreviate it. Now to enter the data, I move the cursor down into the body of the list. The notation here has changed from simply VEL equal, which would be the whole list, to VEL of 1, which is the first entry. Now if I press enter, the cursor moves down here to the formula bar, and I can start entering the data values one at a time. So I'm just going to, oops, that didn't work out right. I'm just going to do that. So let's see, 2.45. I won't say all the numbers. You can just you can see them on the screen. Oh, I made a mistake here, so I'll just delete those. Uh, okay, the velocity data is now entered. I'm going to go back and insert another list, second delete, second alpha to alpha lock. And actually, I think I'm just going to name this out. So we have VEL and OUT, output and velocity. I press enter to create the list. And now again, I'm going to enter the data values for the output data one at a time. And I'm just going to go back through them one time because I know that you're probably going to be checking my results on my calculator. And if you're not seeing the correct numbers, that wouldn't be a good thing. So I'm just going to go backwards up through these data values I've entered in both lists and double check. Okay, that all looks correct. So first thing, I'm just going to jump right into a scatter plot, and I'm going to do a scatter plot on just the raw data, the data that's given. And this is often just the first step in starting to think about linear regression, kind of a relationship between data sets. Uh, Keep in mind the shortcut here to get the correct scaling on the axes is just a zoom stat. I can press the number 9 to get to execute that quickly. Now, if we look at this data scatter plot and think about it carefully, we notice how this is a growth situation. In other words, as the wind speed or wind velocity increases, it's true that the output voltage is also increasing. But notice how the curvature here is different. Here we have a curvature that's opening downward. And in terms of the type of growth that we have, that tells us something. The exponential growth, if this were exponential growth, the curve would start out like this, along, kind of skimming along the x-axis, and then it would begin to turn upwards like this and keep on going. And notice that shaped curve would open upwards. This type of curve, though, is doing something different. It's opening downwards. And so what's actually happening here is, as the wind speed increases, the output voltage also increases, but it begins to flatten out as it grows. Which makes sense because there's a limit to how much voltage the generator can possibly create. And so regardless of wind speed, at some point, that voltage is going to level off, and that's what we see happening. So this is not exponential growth. So this is a different type pattern than what we would see or what we saw in the moisture depth data set. Now, just for completeness, just to be complete here, I'm going to go ahead and do a LinReg t-test on this data set as well, on these two data sets, which is part of what you're being asked to do on the activity. And I'm going to kind of go through it a little bit quickly here. As I said, this is review, at least this part of doing the LinReg t-test. It was covered in previous videos. I'm going to choose an alternate assumption of greater than here because this is growth, not decay. And we might as well store the regression equation in Y1. I'll choose calculate, and these are the numbers you should be seeing for the activity. Very small p-value, strong evidence that we should reject the null hypothesis of no linear positive relationship. And the R-squared is showing about 87% of the variability in the voltage output can be attributed to the wind speed using the linear model. So all of this stacks up really nicely in favor of using a linear model. It's only when we get to the scatter plot of the residuals, and I'm going to turn this equation off here for the time being, and I'll go into, let me reconfigure the stat plot window, and the residual plot is always the x-list plotted against the residuals. And zoom 9 again to rescale. Now this is the classic curvilinear pattern that's talked about in section 13.4 of the textbook. And this indicates that the linear model is perhaps not the best fitting model, or it's not the best fitting model. And if we go back and look at the scatter plot of the raw data one more time, we can begin to see why. And I know I'm kind of shifting back and forth here between graphs, but I just want to make these points. And I'm just doing this rather quickly. Zoom 9 again to rescale. So notice there's what the best fit line looks like for this data set. And you can see systematically that the data values, or the points, start out below the line. Systematically, they cross the line, they stay above the line. This one's kind of below the line, perhaps here. It's sort of an anomaly, but the general pattern is for the residuals to start out, or I'm sorry, for the outputs to start out below the linear line and then rise above that line and then fall back below again. Now this is again not a linear pattern. So to linearize the data, what we need to think about is what might that pattern be. And this actually looks like a logarithmic pattern to me. Logarithmic growth. Starting off rather quickly and then flattening out. The growth rate is slowing down, or the growth is slowing down. So the transformation that we need to do on the Y data is a different transformation. So I'm going to go ahead and clear this out actually, because I'm going to redo the regression analysis. I'm going to go back into the editor, the data editor, press stat, choose edit. And right next to the output data set, I'm going to insert a new list. And I'm going to call that list ln for the natural, or I'm sorry, let me take that back. I'm going to call this the, I'm going to exponentiate the data. Since the pattern in the scatter plot is logarithmic, I'm going to apply the inverse of that logarithmic pattern, which is an exponential. So I'm going to use e to the x here. That's a second function. Press the ln key. Oops. Oh, I need to name the list. Hold on a second. Okay, so go back to that step. Second alpha to alpha lock, and I'm going to call this L in OUT. Which is the, I keep doing that. It's not the natural log. It's that's what everybody wants to do. It's the exponential. So I'm going to call it E. Maybe I'll just call it E out. E of out. All right, there we go. And press enter one more time. Cursor comes down. And I'm going to go second ln for e to the power. And what I want to put in that exponent place is going to be the output data. So I go back to the second stat to get back into the list of all the lists on the calculator. Now, this is a newer generation calculator I'm using here. And so if you've got one of the older calculators, this works the same way. It's just that the notation looks different. So this will be E with a parenthesis here, and then you put the L output into that parenthesis and then close it. With the newer calculator, I just do a right arrow key to bring the cursor back down onto the main function bar line, so to speak. Well, in any case, I'll press enter now, and what the calculator's just done is exponentiated all of the output values in the output list. When we go back to the scatter plot now, I'm not going to look at velocity versus output. I want to look at velocity versus the transform data. And I'll do a zoom 9 to rescale the window. And notice this looks much, much more like a linear pattern. So the next step would be to do a LinReg t-test on this transform data. And we see the p-value is even smaller. It was very small in both cases, so there's definitely significant evidence there's a relationship between these variables. But notice here the r-squared value definitely improved. More of the variations being explained by the nonlinear model than the linear model. 96% compared to about 87 or so percent. Now I want to show you something, just kind of a calculator trick here. There's a lot of algebra involved if we were going to do the transformation back to the proper logarithmic function that we would use here. And so what I want to do is just show you kind of like I said, a calculator trick to get around all of that algebra. I'm going to go back now to the original scatter plot of the raw data. That's just the velocity versus output. And I'm going to define y equals differently. Now this is fitting. This is a linear equation, but it's fitting the exponential function of y equaling the linear function. And I'm not sure that makes a lot of sense right now, but take a look at this. If I take the natural log of that equation that I had the calculator store in y equals, and I'm just gonna take some of these decimals out. The calculator gives us so much accuracy, it's kind of almost absurd sometimes. So if I take a few of those out, those decimal places, it's still highly accurate, but easier to see in the view screen. So notice what I'm doing is I'm taking the natural log of the line of best fit. And this is really not an equation, it's an expression, I understand that, but the equation is y over here equal the natural log of this linear part. And I'm just going to do a zoom 9 to rescale the window. So notice how now I have the right kind of a curve fitting that line. And in fact, if I wanted to make predictions now, I could just trace. Right now, when I press trace, I can see I'm tracing plot 1, which is velocity versus output. So I can jump from one of the observed values in the scatter plot to the next. But I want to actually be on the curve. So if I do an up arrow, now notice that my cursor is tracing on the actual curve. So if I wanted to make a prediction now for, say, the voltage output when the wind velocity is, say, 7 miles per hour, if I just type in a 7 and press enter, I see that the generator would be producing about 1.94 volts. And again, I'm right on the line. So what I'm trying to illustrate here is instead of going around and doing all of that really fairly, I guess it's not terribly difficult, but it's technical algebra work to transform the equation from a logarithmic relationship to an exponential and back and forth, what we can do is use the calculator and approximate these values. And say I'm interested then in the voltage output when the wind speed is 3 miles per hour. I could just type a 3 and see that it's about 7.84. And so again, the cursor is tracing on that curve. So any of those x values, any of those wind velocities that I want back the logarithmic prediction of the output, I can just simply use this calculator trick. It works the same way incidentally for the moisture mud example. It's just that we took the natural log of the y data there. So when we got the linear form back from the regression, we would take the exponential of that linear function rather than the log like we did in this case. Anyway, I hope this video kind of clarifies. The main purpose was to show the steps and how to do the transformation on the calculator.